Jai Hind. In this lecture of the subject Electrical Machines 2, KEE 503, I am going to discuss some more numerical questions based upon three-phase induction motor, one based upon three-phase induction motor equivalent circuit, and another one based upon the no-load and blocked rotor test on single-phase induction motor. So, starting with the question, a three-phase star-connected 400 volt, 50 Hz, 4-pole induction motor has the following constants in ohms per phase referred to stator. What are the constants? The constants given are R1, X1, X2, R2 and Xm. They all are in ohms and this is the per phase value of these parameters. These parameters are actually the equivalent circuit parameters of the machine and they all are referred to the stator side. I mean to say the rotor circuit resistance and reactance are referred to the stator side. The machine is star connected, that is the stator winding of three-phase induction motor is connected in star. 400 volt is the line voltage given to the stator winding. So the per phase value of the voltage must be 400 divided by root 3. The machine is getting a supply having frequency of 50 Hz standard as per our country and the number of poles for which the machine is wound is 4, right? Now let us see what all needs to be determined here. We are given with the equivalent circuit parameters, so all the parameters of the simplified equivalent circuit, that is R1, X1, R2, X2 and Xm, where Xm is the magnetizing reactance, R1 is the stator winding resistance per phase, X1 is the stator winding leakage reactance per phase, R2 is the rotor resistance per phase and X2 is the rotor winding leakage reactance per phase. Xm, as I told, is the magnetizing reactance. Besides this, the fixed losses, that is core, friction and windage losses are given as 400 watts. So core loss is combined with the friction and windage losses and collective constant losses are given to us as 400 watts, right? We need to determine the stator current, the output torque and the efficiency of the machine at the operating slip of 4%, that is at the operating slip of 0.04, right? Answers I have mentioned over here. Now let us see how to solve the question. The question is asking for the stator current, the output torque and the efficiency, right? For determination of stator current, let us think about the equivalent circuit first. All the parameters of the equivalent circuit are given to us. So let us now first draw the equivalent circuit as per the data given in the question. So I have got R1, then X1, then I have got magnetizing reactance Xm, then I have got the rotor winding leakage reactance and then I have got the variable rotor circuit resistance in the equivalent circuit as R2 by S, right? This is JXM, this JX2 and the value of X2 is given as 0.45 ohm. So J 0.45 ohm. Xm is given as 28.5. So it is J 28.5 ohm. Then we are having resistance R1 as 0.15 ohm and JX1 as 0.45 ohm. Resistance R2 is given as 0.12. So I can replace this by 0.12 divided by S and the operating slip of the machine for which we need to calculate we need to solve the question by solving the equivalent circuit is given as 0.04. So the value of this variable resistance at the operating slip of 4% comes out to be 0.12 divided by 0.04, right? The applied voltage, the machine is rated for a voltage of 400 volt. So voltage here would be 400 divided by root 3, right? as we all know that the equivalent circuits are drawn on per phase basis and all the calculations are carried out on the per phase basis only, right? Suppose these two terminals, let me just change the color of the ink. Suppose the two terminals are A and B, right? I need to determine the current flowing here. This is the stator current I1. If you see the equivalent circuit, you will find that this circuit is nothing but a simple series parallel RL circuit only, right? And we need to determine the input current to this RL circuit, right? So for determination of current, voltage is known to you, all the parameter impedances are known to you. So if somehow we can calculate the total impedance as seen from the input terminals, we can very well solve the question for determination of the stator current, which is nothing but the input current to this circuit, this RL circuit. So you can see that impedance ZAB is the equivalent of this. So what I'm having in the stator, it is 0.15 plus J 0.45. I hope you agree. Plus the parallel combination of these two branches. One branch is this, second branch is this, right? So parallel combination of these two branches. In these two branches, I can write it is 0.12 upon 0.04 plus J 0.45. It is connected in parallel with an impedance, reactive impedance of 28.5. So the equivalent parallel can be determined as this impedance multiplied by J 28. Here it is for J 20 multiplied by J 28.5. Let me rub this additional part here, right? So in numerator and in denominator, it would be the summation of the two branch impedances. So I can very well write it as 0.12 upon 0.04 plus J, the imaginary part of this entire loop. So it would be 28.5 plus 0.45, right? So this is the equivalent impedance, and solving this, it comes out to be 3.02 plus J 1.188, this much ohms, right? Now the same impedance in polar coordinates can be written as 3.25 magnitude with an angle of approximately 21.47 degrees. So this much ohms. So we have got the equivalent impedance as seen from the input terminals of the equivalent circuit as this value ZAB. Now let us calculate the current. So the current I1 can be calculated as simple voltage divided by the impedance ZAB. What is the voltage? The per phase value of the voltage is 400 divided by root 3, as the stator winding of the machine is connected in star, it is given in the question, divided by 3.25, the magnitude. So in magnitude, the current comes out to be, it is given over here, 71.06. Let us consider the impedance angle as well, 21.47 degree it was. So I can write down the value of current as 71.06 with an angle of minus 21.47 degree, right? So we have got the input current flowing in the circuit. Further, knowing the power factor angle here, I can very well write down the power factor, input power factor of the machine as cosine of 21.47, which comes out to be equal to 0.93, 0.93, right? Now further proceeding. So first part of the question we have calculated. It is the stator current flowing in the circuit. Now we need to proceed for determination of the output torque. Okay, what is the output torque? The output torque can be determined as the output power available at the shaft, that is the shaft power output, divided by the speed of the rotor, right? The operating speed of the rotor in radians per second, that is omega r. So we will calculate omega r later on. Let us now try to find out how to reach at the output. I mean to say how to determine the shaft power output for the machine. So for determination of shaft power output, let us proceed in a way. Let us determine the stator I square R losses. Let us determine the stator input, as now the stator current is known to us. Knowing the stator input, stator power input, and knowing the stator I square R loss, right? Stator power input minus the stator I square R loss will give me the power which is transferred from the stator to the rotor, right? So the power which is transferred to the rotor is said to be the air gap power PG. Once the air gap power PG is known to us, we can very well determine the mechanical power. The mechanical power is given as PG multiplied by 1 minus S, where S is the operating slip of the machine. Okay, so starting with determination of stator input and the stator I square R loss. So stator input can be written as root 3 V I1 cos phi, right? So root 3 Vi cos phi. Here V and I are the line values. The line value of voltage is very well known to us. It is 400 volt, and as the stator winding is star connected, so the line value of current and phase value of current are same, and we have already calculated the phase value of current. So the stator input can very well be written as root 3 multiplied by 400 multiplied by 71.06 multiplied by the power factor, which is 0.93. Solving this, we get the total stator power input as 45.784 kilowatt. 45.784 kilowatt, right? So this is the stator input power. Now let us determine the stator I square R loss. So stator I square R loss, stator I square R loss can be determined as thrice I1 square R1. Resistance R1 is known to us. It is given in the question. So I can very well determine the stator I square R loss as thrice 71.06 square multiplied by the resistance 0.15. And solving this, we will get the stator I square R loss in kilowatt. Directly I am writing the value. It comes out to be 2.272 kilowatt. 2.272 kilowatt. Of course, for determination of the value in kilowatt, you have to divide this entire power by the 1000. Likewise, as I have written the value in kilowatt here as well, so I must divide whatever I have written over there, I must divide it by 1000 to get it in kilowatts, right? So the two values, 45.784 kilowatt is the stator input, and other one is 2.272 kilowatt is the stator I square R loss. So knowing these two, I can very well determine the power input to the rotor. Power input to rotor, which is also said to be the air gap power denoted by PG. So air gap power PG can be written as stator power input minus stator I square R loss, right? The stator power input value was 45.784 minus the stator I square R loss value was 2.272. So this much kilowatt, it comes out to be, upon subtraction, it comes out to be 43.512. So 43.512 kilowatt is the power input to the rotor. Now, knowing the power input to the rotor, I can very well calculate the mechanical power, internal mechanical power developed, right? So the internal mechanical power developed in the machine can be determined as PG into 1 minus S. PG is known to us as 43.512. 1 minus the operating slip was given as 0.04. So 1 minus 0.04, and solving this, we'll get the internal mechanical power developed as 41.77 kilowatt. 41.77 kilowatt. Now, knowing the internal mechanical power developed, I can very well determine shaft power output as PM. Let me write here in short, PM, that is internal mechanical power, PM minus the losses given in the question, that is the fixed losses. So PM minus fixed losses, right? So PM is 41.77 minus the fixed losses were given as 400 watt or 0.4 kilowatt, right? So solving this, I'll get the the shaft power output as 41.37 kilowatt. Now, knowing the shaft power output, what I can determine? I can very well determine the output torque. So, output torque equals to PSH. PSH is the shaft power output divided by omega R. The value of PSH is 41.37 divided by omega R. Omega R can be written as omega S into 1 minus S. Now, what is omega S? Let me tell you. Omega S equals to twice pi ns, where ns is the speed in RPS, speed of the rotating magnetic field in RPS. So it can be written as twice pi. Ns itself can be written as twice F upon P. In our question, the number of poles given are 4 and the frequency is 50 Hz. So I can write it as twice pi multiplied by 2 into F, that is 50 divided by 4. So I'm left with 50 pi, right? 50 pi. So omega S can be written as 50 pi here. So 41.37 divided by 50 pi 1 minus 0.04. Remember that as I was using the power in kilowatt, I was using the unit for power in kilowatt. Here for determination of torque, I must convert this into the watts. So solving this, you will get the shaft power output as PSH upon omega R. You will get the shaft power output from here, and the value of the shaft power output is given as 274.34. 274.34. This much Newton meter. The last thing is efficiency of the machine. So efficiency of the machine is PSH upon stator power input, power output upon power input. So PSH upon P input PSH with us is equal to 41.37 and the P input was equal to 45.784. So 45.784 multiplied by 100 to get it in percentage, and solving this you will get an efficiency of 90.37%. Right? So in this manner you can very well solve this question and also such type of questions. For any query, please write in the chat. Let us consider another question of which is based upon the no load and block rotor test of single phase induction motor. So the test data is like this. The following data relates to tests on a 110 volt, 150 watt, 50 hertz, 6-pole single phase induction motor. The no load test data is given as 110 volts, 63 watt and 2.7 ampere. The block rotor test data is given as 55 volts, 212 watts and 5.8 amperes, right? So the machine is rated for 150 watt. It is getting a supply. It is rated for a supply of 110 volt 50 hertz and it is a 6-pole single phase induction motor. You know that no load test is performed at rated voltage. So the no load test data, rated voltage, the power consumption under the condition of no load and the no load current. The block rotor test is performed at rated current. So the rated current of the machine 5.8 ampere, 55 volt and 212 watts are the block rotor test condition, voltage and power consumption by the motor respectively. The stator winding resistance is given to us as 2.5 ohms and during the block rotor test the starting winding is kept open. What is the meaning of the starting winding is kept open? You see, block rotor test, during block rotor test the rotor remains at standstill though supply is given to the motor. If we keep the starting winding or the auxiliary winding of the machine open circuited, rotor will not at all rotate, right? Because no starting torque would be developed. The condition of short circuit actually prevails in the equivalent circuit under these conditions, right? So if we keep the auxiliary winding or the starting winding open, we won't require any arrangement for externally blocking the rotor of the machine, right? So we have to find out the equivalent circuit parameters and also the core friction and windage loss. The core friction and windage losses comes in the category of fixed or constant losses. So basically we need to determine the fixed losses and the equivalent circuit parameters, right? So let us proceed with block rotor test first for determination of the equivalent circuit parameters. The equivalent circuit of single phase induction motor under block rotor condition can be drawn like this. You can see that the branch corresponding to XM magnetizing reactance is ignored here. Why so? Because as the voltage under block rotor condition is very low, the flux will also be low and we can neglect this particular branch. The neglection will not result in much difference in the calculated value. So under these conditions, when it is possible, then we neglect the we can have certain approximations if the approximations are not going to affect the result much, right? So the parameters which we will determine can be determined by first calculating the blocked rotor test parameters. So blocked rotor test parameters are ZSC, that is short circuit impedance, which is given as VSC upon ISC. So short circuit voltage is known to us as 55 volt. The short circuit current is known to us as 5.8 amperes. So solving this, we can calculate ZSC. Kindly calculate it. You will get the value in ohms, right? Then under blocked rotor condition, the resistance RSC from the test data can be determined as WSC upon ISC square. You know that well, that WSC equals to ISC square into RSC, right? So I can very well determine RSC as WSC upon ISC square. Now, you see the equivalent circuit to know what would be actually RSC. So, total resistance under this condition in the equivalent circuit can very well be seen as equal to what? R1 plus 2 times of R2 by 2. So, simply it is RSC. So, simply it can be written as R1 plus R2. So, R1 plus R2 and the value of RSC is known to us. So, I can very well calculate resistance R2 as RSC minus R1. So, RSC can be calculated from here. WSC is 212 watts and ISC is 5.8 amperes. So, 212 divided by 5.8 square will give me resistance RSC. I'll share the answer key as well in the last slide of this. So, I can very well calculate R2 from here. RC is calculated from here, 212 upon 5.8 square minus resistance R1, and resistance R1 is given to us as 2.5. So, solving this, you can very well calculate the value of resistance R2, right? Now, knowing ZSC and knowing RSC, I can very well calculate XSC, right? So, what would be XSC? XSC would be equal to under root ZSC square minus RSC square. So, from here, I can calculate the numeric value of XSC. Now, let us see in the equivalent circuit, let us see what would actually be the short circuit reactance under this condition. So, what I can see over here, it is the summation of X1 and X2 by 2 and X2 by 2. So, simply XSC is equal to X1 plus X2, right? XSC is equal to X1 plus X2. Now, there is no way of separating the reactances X1 and X2. X1 and X2 are the reactances, cell leakage reactances of stator and rotor winding respectively. So, the common practice is to take them equal. So, when we take them equal, from here, I can very well write that X1 would be equal to X2 and it would be equal to half of XSC. So, simply I can write X1 equals to X2 equals to half of under root ZSC square minus RSC square as given by this equation. Okay. So, all this I have already told. Now, let me give you the values over here. So, XSC comes out to be 7.08, right? R1 is 2.5, R2 comes out to be 3.8. Let me write down these values over here. R2, 3.8. XSC came out to be, let me just check the value. XSC, 7.08. So, 7.08 ohm, right? And knowing XSC, I can very well calculate X1 equals to X2 equals to 7.08 divided by 2. So, it can be written as 3.54. 3.54 ohms. So, I have got R1, I have got X1, I have got X2, I have got resistance R2. Resistance R1 is given to me in the question itself. So, the only thing left is the magnetizing reactance XM now. The magnetizing reactance XM is calculated from the no-load test data, right? The no-load equivalent circuit of the machine can be drawn like this. Under no-load condition, the operating slip S is very, very small, nearing to 0. So, resistance R2 by S can be neglected from here in comparison with XM by 2, right? And in comparison with this particular branch, this branch was originally I mean to say this parameter was originally R2 upon 2 into 2 minus S. S is approximately equal to 0, so it reduces to R2 by 2. R2 by 2 into 2, that is R2 by 4. So, R2 by 4 plus X2 by 2. In comparison with this impedance, the Xm by 2 impedance is quite high. So, in this parallel combination, in this parallel circuit, it can be neglected. So, this results in approximation of the equivalent circuit under no load condition by the circuit which is drawn over here. I only need to calculate the value of Xm now. All other parameters I have already calculated from the blocked rotor test data, right? So, for this, let us now proceed. For determination of Xm, actually, I have to calculate XNL, which is the no load impedance of the impedance offered, the reactance offered by the equivalent circuit under no load condition, right? So, for this, let us calculate cos theta NL. Cos theta NL is the no load power factor angle, no load power factor of the machine. I can very well calculate ZNL as V1 upon INL. What is V1 over here? The no load test data. V1 is the rated voltage. What about the INL? It is the 2.7 ampere current. So, solving this, I can very well calculate ZNL. Knowing ZNL, I can calculate XNL as ZNL sine theta NL. So, I can write it as 110 upon 2.7 sine of cos inverse theta NL, right? So, from here, I'll get the value of XNL. That is okay. We know that ZNL, which is the total impedance offered or the total impedance seen from the terminals of equivalent circuit, the equivalent circuit which is drawn for no load condition. This is ZNL. From the equivalent circuit itself, I can see that ZNL can be written as R1 plus R2 by 4, R1 plus R2 by 4 plus JX1, XM by 2, X2 by 2. The same thing is written over here, right? Now, we know that ZNL can be represented by RNL plus JXNL. It means the right hand side and left hand side imaginary terms, right? They are equal. So, I can write XNL equals to X1 plus half of X2 plus XM. Do you agree? So, from here, let me give you the values here. The cos theta NL is calculated, sin theta NL is calculated, ZNL is calculated. Knowing ZNL and cos sin theta NL using the previous equation only, I can very well write down the value of XNL as 40 ohm, right? Knowing the value of XNL as 40 ohm, I can very well write down, I can very well solve this equation. X1 and X2 are known to me. The only unknown here is Xm. So, the Xm is calculated and it comes out to be 69.38 ohms, right? So, we have got the last parameter Xm as 69.38 ohm. One more thing that was required to calculate in the question was the core friction and windage loss. So, the core friction and windage losses can be determined using WNL equals to, let me show you here. If we subtract the I square R loss taking place during the no load test from the total power consumed by the motor, total power taken by the motor from the supply, we will get the constant losses. Under no load condition, total losses taking place in the machine are the constant losses and the amount of I square R loss. Because the no load current in induction motor is quite high, we cannot neglect the presence of no load current during the no load test. Okay. So, to get the constant losses, we have to proceed like this. From equivalent circuit, you can very well see that the total resistance under no load condition is R1 plus R2 by 4, right? So, WNL can be written as constant losses can be written as WNL minus INL square R1 plus R2 by 4. We are having all these values, R1 as well as R2 we have calculated. Solving this, you will get the constant losses amounting 37.85 watts, right? So in this manner, you can solve this question and the similar question of single phase induction motor based upon the no load and blocked rotor test data. So that is for all for this lecture. Thank you.